This is Neil from Anabit, and welcome to using the two-point calibration method to increase digital to analog converter or DAC accuracy. Okay, here is the agenda for this video tutorial. First, we're going to do a quick overview of DAC offset and DAC gain error. These are common DAC specifications that you'll find in the datasheet for any DAC IC. We're going to go over steps for performing the two-point calibration, which uses the linear slope and point slope formulas that you probably learned in algebra years ago. Then we're going to see our calibration process in action. So we're going to see a demo of this, and we're going to see how it greatly improves the accuracy of the DAC. What we're going to use for our demo is Anabit's reflex DAC family. And there's two versions of the reflex DAC family. We're going to use the negative 4.096 volt to positive 4.096 volt version. And the reason I'm going to use the reflex DAC family is because to get that bipolar output from the DAC, because the DAC is just a unipolar DAC, we use a summing amplifier. So what's nice is an amplifier also has some gain and offset error. So basically, we're going to be able to calibrate not only the gain offset error in the DAC, but also in the summing amplifier, right? So this approach doesn't just correct the DAC, it corrects other factors in the DAC's output signal conditioning path. And then to finish up, we're going to look at DAC error contributors that the two-point calibration does not correct. Okay, let's look at DAC offset and gain error. Okay, here we have a chart of a DAC transfer curve. So this is a 4-bit DAC, and the orange staircase line represents the DAC output steps. 4-bit DAC means 2 to the 4. We have 16 different output codes we can do for the DAC's output. And then the blue line represents the ideal curve of the DAC. But every DAC has a little gain error and a little offset error. So the offset error is in green, right? So this is going to be a constant value that's different from the ideal curve, right? It could be 500 microvolts, could be negative 100 microvolts. And that error is always going to be there when you output from the DAC. Then we have the gain error. Gain error typically is very low at the low end of the DAC and then is going to deviate from the ideal curve as you go up in codes. But notice, both these error curves are linear, right? So the two-point calibration is dependent on correcting error that's in linear form. Okay, let's go step by step through the process, and then we'll see the process in action. So first thing you want to do is you want to power up your circuit and let it warm up. The reason you want to let it warm up is because DAC, or if you have an op amp on the circuit, they're going to have some kind of temperature coefficient spec. And the idea is when you first turn on a circuit, current's flowing. It might be very little current, but current's flowing, and the board may change temperature just a little bit, right? So we don't want to make calibration measurements when there's temperature drift occurring. So let's let it stabilize first. Then we need to pick our 2 points, right? And we can pick them as codes or we can pick them as voltages and then convert them to codes. The idea is you don't want to pick 2 points close together, right? Because you want to be able to accurately capture that curve. So typically what you do is you do about 10% and 90% of the full scale range. You know, if it's unipolar, that's really easy to calculate 10 and 90. If it's bipolar, which we'll use in our example, you could do, negative 40% of mid and positive 40% of mid. 80% in the middle of 100% range gives us 10 and 90. Next, we want to measure each of our points with a high accuracy measurement device, right? We need to find a measurement device that has much less uncertainty than the DAC's output, right? And so you want to probably get at least 3 or 4 times better uncertainty in your measurement device than the DAC. And then, of course, with our measurement device, we should try to average readings together, right? And that'll take out some low frequency noise in the readings. And you can use a voltmeter, you can use a digital multimeter or DMM, or you can use a high accuracy ADC circuit. For our example, I have access to a very accurate DMM that we'll use for our test. If you don't have access to a very accurate measurement device, you can use an ADC circuit. And in fact, Anabit offers an open source reference design of a precision multimeter, which has really good accuracy specs and 32 bits of resolution. So that could be something you could use for a calibration process like this. So next we want to record our 2 readings. So how do we do that? We have to come up with the DAC code that's 10%, enter it in the DAC, we get our output, we measure that voltage, right? That's our first voltage, then we repeat that for our 90% spot and record that voltage. The next step is where the math comes in, right? So this is where we're going to use the slope formula and the slope intercept formula. If you're not familiar with those, I'll provide a link in the video description, and then we're going to model the resulting behavior. So what we're going to try to do is we're going to get A, which is the slope, and B, which is the offset, right? Because those are the two error values we're correcting for. The slope equation you can see with A, and the offset equation you can see with B. So A and B is what we want to put in our code, right? This is what we're correcting in software. And then when we output from our DAC, we need to use the equation shown with C command. It should sort of be C code. But you can see VREC is the voltage you want the DAC to output, but the DAC is not perfect. There's some offset and gain error. So that's where we're going to plug A and B in. So now we have A and B stored in our code, and every time the DAC is going to output a value, we pull those values, we do this calculation to correct to the actual voltage we want to get. All right, let's look at a demo to see this in action. Okay, here you're looking at a zoomed in picture of the Reflex DAC. This is the 4.096 plus or minus volt version. On the right, those black and red connectors are connected to my DMM. The red and black on the other side is the power supply, and then the wiring is for the SPI communication to set the DAC to the outputs. And you can kind of see, here is the DAC, here is the summing amplifier, and here's our voltage reference. So let me turn this on. So first we're going to look at the uncorrected value. So we're going to do negative 3.3 volts and positive 3.3 volts. They're not exactly 10% 90, but they're close to it, and 3.3 volts is an easy number to work with. So that's why I try to do that for this demo. So this is the uncorrected version. So we would use this value in those equations I just showed, and then we would do it for 3.3 volts and negative 3.3 volts. For the sake of time, I've already done both measurements. And what I did is I have code where I can turn on and turn off the calibration. So I did my warm-up time, I made my measurements, I did my calculations, and I put those in code. And by the way, the code that I'm going to show in this video, the Arduino code, I'll give a link in the video description so you can access it on GitHub to see how I did it. So this is the uncorrected value. And you can see we have about 5 millivolts off. So we do have some error there. Now here is my code. And remember those equations we did, A and B, here's the result, right? And I'll tell you, one of the reasons I'm showing the 3.3 volts and not the negative 3.3 volts is because there's actually not much offset error. There's more gain error. So you see a lot more error as you go higher in voltage. Then here's my setting right here, 3.3 volts, and you can kind of just see some of my notes here. And this will be available for download, as I mentioned already. So let me turn this back on. Here, now what I'm going to do is I'm going to turn the calibration enable to 1, right? So this now means that the calibration will be executed by the DAC in the code when I upload it to the DAC. So here we're uploading it. I'm going to pause it 1 second. You're going to see this slowly change. That's because I'm doing a lot of averages in the DMM. So I just uploaded it, and now you're going to see the DMM's value slowly go up and stabilize because I'm doing a lot of averages. Look at that. We're basically at 3.3 volts. So we're seeing about what? We're seeing about 200 microvolts of error right there, right? And that's probably quantization error. So you can see this calibration can greatly increase the accuracy of your DAC output. Okay, let's talk briefly about error contributors that the 2-point calibration does not correct. The first one is quantization error. And quantization error is the effect on accuracy due to limitations in resolution, right? By nature, digital signals are not infinite, so these are going to be finite, so you're always going to have quantization error. And for this example, our range is like, 8 point some volts and change, and we have a 14-bit DAC. So our quantization error is about 250 microvolts. So if you remember that reading we had about 200 microvolts. Now, 250 microvolts, of course, is the max quantization error. So you can see that the error that we still saw in the DAC's output was probably mainly quantization error. Other error factors are integral nonlinearity or differential nonlinearity error. Since this error is nonlinear, 2-point calibration is not going to eliminate them. There's also dynamic error and distortion. This is error that more shows up in AC signal outputs. I'm not going to get into the details, but they're not going to be taken out by a 2-point calibration. And then, of course, noise. Noise is also going to be sort of a dynamic changing error. The 2-point calibration method is good for linear static error. It's not going to capture changing error. And of course, there's temperature drift, right? So temperature drift is the change in the output due to the change in the temperature. Now, you can use the 2-point calibration method to handle that. You just have to do a table of 2-point calibration values and be able to measure the temperature around your DAC and apply the right correction factors. But once again, these other error factors, especially when you're doing a DC output, are very minimal, and we can't get rid of quantization error. So you can see that the 2-point calibration method really corrects the output of your DAC. That's it for this video. If you have anything to add, please use the comment section. If there's anything I missed or anything other insights you want to add, please do, and please check out anabit.co.